Let's look at how to deal with pressure forces over more complex geometries where we don't have a nice simple vertical or horizontal wall, and we may need to deal with some curvature or other variations. For example, what would we do on a sloping surface? We've got this surface which starts down here 4 meters under the water and slopes off in this direction, and it takes 5 meters running in this direction to rise up those 4 meters. And we'd like to integrate the pressure forces that are acting on this surface. Well, the concepts all remain the same, but we need to set up our calculation regime so that our life will be a little bit easier. So if you can pick one axis to align, then let's pick one of them. I'd like to make my life easier to integrate over this surface by picking an axis that runs right along the surface. Let's call that the y-axis. Now we've got the complication here that y doesn't match up exactly with depth under the water. But we could make the origin here for the y-axis, so there's my x-axis. So I can integrate over this surface to get forces in the x direction. I'll need to figure out what the pressure is in terms of y though. So from Pythagoras, 4 squared plus 5 squared, square root, I find that that location there, that's where y is equal to 6.4 meters. So if I was progressing along the y-axis from here up to the surface, I would be going from 0 to 6.4 meters. So my progress would be y over 6.4. That's the fraction of the distance that I've gone along here. Now the pressure down here is rho g times 4. The pressure up here is 0 if I'm using gauge pressure. So if I construct my pressure as 4 rho g times 1 when y is equal to 0, or times 0 when y is equal to 6.4, then that will be my pressure as a function of y. So you're going to have to brush up and make sure that you can do this sort of basic analytic geometry to transform coordinate systems and be able to get your pressures in terms of coordinates that you can use effectively. Always use gauge pressure for simplicity, because that'll allow you to totally ignore atmospheric pressure, which would be acting on the opposite side of the gate, for example. Once you've done that, you're going to have to look at this individual surface that we've managed to pull out now as a free body diagram. We can define the pressure forces acting over that, and if it's a free body diagram and it's not accelerating, it's not changing, it's sitting still, then if we integrate from location y1 to y2, we must have the sum of the forces equal to 0 and the sum of the moments equal to 0. And if we've got it being supported in two locations, say at the top and the bottom, that will be enough information to allow us to solve for those forces. If we have more points of contact, then we'll need to know, as you know from solid mechanics, something about the flexibility of this surface, and we won't worry about that in our fluid mechanics course. Now, what about if you've got a curved surface, a surface like this? Well, you're still going to be subject to all of the same rules about the sum of the forces and the sum of the moments being equal to 0. You're still going to have to consider the sum of the forces in the x direction, but now we've got a two-dimensional directionality to our forces. So we'll also have to say that not only are the sum of the forces in the x direction equal to 0, but the sum of the forces in the y direction are equal to 0. That didn't tell us anything interesting in this one because there aren't any pressure forces acting in the y direction. But if we consider a small incremental area on here, and we consider our pressure force acting perpendicular to the local surface dimension on that area, then we'll have this force, which we can break into components in the y direction and the x direction, and we can use our integration over the entire surface to sum up all of the forces acting in the x direction. Up here, more projected area, the force is acting in a different direction, and we'll need to know the details of the curvature to be able to tell what that direction is, but we can still break it into a y component and an x component. Likewise down here, where our area is facing off in that direction, we've got a pressure force acting in like that. It's still perpendicular to the surface, and now it's got a very small y component and quite a large x component. So the sum of the forces in the x direction we can get by integrating over the entire surface here. So we'll need to integrate over the surface the force, which will be the pressure times the normal vector, and because a normal vector points outwards, we'll have a negative sign, times dA. And when we go to break that down, we'll break it into components, and we'll break it into the force due to pressure in the x direction being the integral over the area, P times dAx, and the force in the y direction being integral over the area, P dAy. So hold on to that idea, and we'll use that capability in some examples in a little while. Now, this will allow us to find pressure forces acting on static systems. This is also going to turn out the same idea of being able to integrate the pressure over a surface to be important later on when we look at airfoils, for example. For example, wings on aircraft or blades on wind turbines, just about any system like that. If we have an airfoil like this and a flow coming on in this direction, we'll see a much lower pressure on top and a higher pressure on the bottom, and the result will be that we can integrate the difference in these pressures acting in the directions that they act on the surface, and when we integrate all of that pressure, we'll wind up with lift. So this kind of application will show up later on when we're looking at airfoils and when we're looking at wings on wind turbines and things like that. So keep in mind, you're going to need to be able to do the analytic geometry to sort out pressure as a function of location and y. We'll see some examples later on where we need to follow around and keep track of both components of direction. And we'll be integrating pressure over areas for all sorts of applications later on in our fluid mechanics studies.